Hello, in this short video we talk about some fun but very important properties of liquids that we can now fully appreciate because we have an idea of intermolecular forces. So first up is viscosity. Viscosity is a measure of a fluid's resistance to flow. And so you can think of water, okay, you can pour water fairly easily. You can think of honey, that's a lot harder to pour. And honey has a much higher viscosity because there's a greater resistance to it flowing out of the cup into your plate, something like that. So greater intermolecular forces lead to a greater viscosity. If the molecules attract each other more strongly, then they're much less likely to flow, because the process of flow involves breaking these intermolecular forces for the molecules to slide past each other. Viscosity usually decreases as temperature goes up, because if you heat something to a higher temperature, there's more thermal energy in the sample, and then that makes it easier for these intermolecular forces to break as the liquid flows. So viscosity values are determined in poise is the unit, or centipoise is the one we commonly use. Water is in the ballpark of 1 centipoise. Honey is a much higher viscosity value. Acetone is a much lower viscosity, so it flows much more readily. Olive oil is a little higher than water. Things like that. So that's viscosity from a simple perspective. The next step in thinking about viscosity is for molecules like honey, you can have these long chain-like sugar molecules. Now when the sample tries to flow, these molecules will get entangled, and that will further resist flow beyond just what intermolecular forces would tell you. So that's another thing to think about when pondering viscosity. All right, surface tension is next. So surface tension is the amount of energy required to increase the surface area of a liquid. And so let's start with this beaker on the left side here. So each of these circles represents a particle. And now kind of down lower, this particle in the middle here, okay, there's intermolecular forces to each of these other particles nearby. And this is shown in 2 dimensions, but it would exist in 3 dimensions as well. And these intermolecular forces hold the liquid together, but don't exert any net force on the sample. Whereas at the surface here, this particle at the top, it has intermolecular forces to everything below it, but then no intermolecular forces above it because there's no liquid above it. And so this experiences a net force down into the sample. And this tends to pull the surface of the liquid closer towards the center. And in effect, it makes it seem like there's a little membrane on top of the water. And normally you can stick your finger in water, no problem, but you can also very gently lay a paperclip on top of water, and if you do it just right, it'll float there. And then you tap it a little bit to break the surface tension, then it sinks to the bottom. This is the reason why water droplets are spherical, because in the sphere, the water on the surface is getting pulled towards the center of the water droplet, and that tends to form it into a sphere, which minimizes the surface area. It's also why bugs can float on water, because of the surface tension. If they don't weigh enough to break through that surface, then they can just float right on top. And here these examples are for water, but if you have a different liquid, it'll have different surface tension. If you put a drop of acetone on the counter, which has lower intermolecular forces, it will spread farther around on the surface, whereas water will stay in a nice little drop because it has a higher surface tension and higher intermolecular forces. Okay, we should also talk about capillary action, and this is where liquid spontaneously rises in a tube. And the reason it does this is a combination of cohesion, the attraction between liquid molecules, and adhesion, the attraction between the liquid and the wall of the tube. And so for water, water is polar, glass is also polar. You can treat the surface of glass to make it nonpolar, but generally you don't unless you have a need to. And so at the surface here, this water is attracted towards the glass in the container. And if the diameter is smaller, it's attracted even farther towards the glass of the container. And that will cause it to rise up the tube. And if you have a thinner tube, it'll rise farther up the tube. This causes the meniscus in laboratory glassware. And we had to create kind of a standard that, all right, we're always going to read the glassware here at the bottom of the meniscus. And the scale is set up for that. A little arbitrary, but it's also the easiest way to read the level of liquid in this tube. Now mercury, on the other hand, is nonpolar, and so in a polar tube, it'll shy away from the edges of the tube. And it'll tend to make a kind of reverse-looking meniscus, which is pretty cool. All right, and the last thing in this video is this idea of solubility. And this is really important both in terms of chemistry and in terms of biology, which is ultimately just chemistry on a really, really large scale. So the mantra here is like dissolves like. And so two substances with similar intermolecular forces are very likely to be soluble in each other. And so nonpolar molecules will be soluble in nonpolar solvents. Polar molecules will dissolve in polar solvents. And ionic compounds, which are effectively incredibly polar molecules, are much more soluble in polar solvents. And so that's pretty much the idea there. In practice, it can be a lot more complicated, but the idea is still just this simple. So what you have to be able to do is look at a molecule and determine whether it's polar or not. And so if you have a molecule with lots and lots of covalent bonds, well, generally, if you have lots of oxygen-hydrogen, nitrogen-hydrogen, or carbon-oxygen bonds, then this thing's going to be more polar. If you have much less of these bonds, it's generally not so polar overall, and it's going to be soluble in organic solvents instead. And so some examples of solvents here. Gen Chem is almost entirely done in water, so we use that all the time. But when you go to organic chemistry, you start dealing with molecules that aren't water soluble, so you have to use a much wider variety of solvents. So if your molecule is still somewhat polar, you can use ethanol, acetone, acetonitrile. These are all polar solvents. Or if your molecule is not as polar, you can use solvents that are either completely nonpolar or like partially polar. So benzene, the carbon-hydrogen bond, has a very low polarity, and specifically in benzene, it cancels out in space, so this thing is completely nonpolar. Chloroform is slightly polar. The carbon-chlorine bond is not very polar, and the geometry here, you cancel out much of that polarity, but not all of it, so it's a little polar. Hexane is pretty much entirely nonpolar. Diethyl ether, okay, this carbon-oxygen bond in the middle, that's polar. But the geometry here is that you cancel out much of the polarity, but not all, so it's kind of a slightly soluble solvent. Okay, then looking at the molecules that you might want to dissolve into the solvents, let's kind of look at these and get a gauge as to what solvent they'll dissolve in. And so first of all, we're using bond line drawings here. And so how these are set up is that at every intersection of lines is a carbon atom. And then carbon likes to make 4 bonds because when it does so, its formal charge is 0. And so you look at it, so say this carbon atom over here, it has 2 bonds to the right, 1 bond to the left. So that means that there's 1 bond up top, which has a hydrogen attached to it by default in how we show this drawing. We omit all these hydrogens because it's just a lot cleaner. You know, if you were to draw this out with all the hydrogens, it would look like a mess. But if you take them away, it's a lot cleaner and easier to see. So, thinking about the polarity of retinol, most of this is nonpolar. All carbon-hydrogen bonds, which are pretty much nonpolar. There is this OH group on the end, and so that'll affect the polarity very slightly. It's outweighed by the entirety of the nonpolar molecule. And so vitamin A is hydrophobic. And I don't know if we've used this word before, but you can look at it and figure it out. Hydro is water. Phobic means it's afraid of water. Instead, it's soluble in organic solvents that are nonpolar or fats. So you take vitamin A and it concentrates in the fats of your body. And so it's possible to overdose on vitamin A because you take more of it, it just keeps going into the fat of your body and then can lead to some bad effects. In contrast, vitamin C is very polar. There's a lot of OH bonds, and these will hydrogen bond to the water or to ascorbic acid molecules. And so this is very hydrophilic. It loves water. And so it's soluble in water. So if you keep drinking more and more vitamin C, you're just going to pee it out because it's soluble in the water and then your kidneys take care of it. So it's really hard to overdose on vitamin C. Okay, cholesterol tends to stick to your arteries because it's pretty nonpolar. The hydroxyl group in the bottom left, really all it does is it serves to orient it in a membrane. The OH will stick out at the edge of your lipid bilayer and then the rest of the cholesterol will go inside. but generally that's really nonpolar and hydrophobic. And then vitamin B2, riboflavin, is... And there you go. So this idea of molecules and what solvents they dissolve in becomes really important once you move beyond the simple molecules that we deal with in general chemistry. So I wanted to bring this to your attention, and you'll probably have to deal with it again when you take organic chemistry. Because here you're working with a bunch of molecules that are not water soluble. What are you going to do with them? You have to dissolve them in some other solvent. And now you have a bunch of choices. This one's a little more polar, this one's a little less. Maybe this facilitates the reaction better than the other one. And so it's something you have to work with. Okay, that's what we have for now. Thanks for watching, and I'll see you in class.